Hey Lukas!
Hey Jan!
I heard you've joined the NANOCOM project.
Yes, I just joined the team.
Oh, welcome on board. Well, I've got an issue with the molecular communication testbed in Erlangen that our colleagues Max, Jens and Harald are working on. And you might be able to help me.
The testbed where they put magnetic particles into tubes filled with water, just like in this picture I happen to have open here.
Mm-hmm.
Sure, what about it?
Well, they want to figure out if it can be used for network communication.
I don't know. Did you try to model it in a network simulator?
Well, I wanted to, but I didn't know which one to use.
I think Fabian told me about some that might fit here. If the particles are mainly transported by diffusion, can't you just use any of the existing molecular communication simulators?
I would want to, but the testbed has pumps hooked up to the tubes. So I need something that can consider the fluid motion.
Sure thing. Just take a simulator like Nano NS3 or a quad then.
But isn't the flow profile in those circular tubes a little more complex than that?
I think you need something that can use the Poiseuille flow profile, where the water moves slower closer to the tube walls. Don't worry, BINS 2 supports this as well.
I just worry that the actual setup in Erlangen is even more complex, with intersections and several pumps working together.
Well, that's certainly a challenge. All I can think of right now is using a multiphysics simulation. Those allow you to model particles suspended in fluid flows and all kinds of crazy tube shapes.
That sounds good. But on the other hand, won't this take ages to compute if I have a larger system and don't want to transmit only a single bit?
Yeah, that's true. There's got to be a better way. And actually, didn't Fabian also have an idea for a new simulator?
Oh, really? What's it about?
Well, if you assume that particles are carried along with the water flow, you don't need to run a full multiphysics simulation, and instead you can just use a fluid simulator like OpenFOAM, for example, to determine how the water behaves, and then you can add the particles in a second step.
That sounds much faster.
Probably, but no one has tried to do it like this yet.
Oh, well, then that's something we could do.
So, do you have a prototype ready?
Yes, it's nothing fancy, just a few lines of Python code, but I already discovered it has horrible running time. It probably takes hours to simulate just a few bits.
What is the approach you're using?
Well, first I modeled the geometry in OpenFOAM, then I run the fluid simulation, and I export the result as a vector field. Then I import the vector field and use it to determine the flow at the current position of each molecule, and use that to determine how it moves in each time step. In some time steps, I inject molecules at the beginning of the tube, and there's an area at the end of the tube where I count the molecules in each time step to determine the receiver response.
Okay, you should be able to get decent performance out of this. How do you determine the values at intermediate positions?
Well, there's an issue. So, since the fluid simulation only exports the flow at discrete positions of each cell, I need to determine the closest cell for each molecule in each time step. And that means comparing to all the cells in the fluid simulation. And there's like 1 million of those.
Okay, but if you just want to determine the closest cell, saving the vector field in a spatial data structure, for example, like a KD tree, would be more efficient. And a KD tree would allow you to support lookups in logarithmic time.
That sounds good. I'll try that. But I still have issues with choosing the correct time step size. If I choose it too large, the molecular paths diverge, or sometimes they just jump out of the tube entirely.
Isn't that a pretty old issue inherent to discrete integration of functions?
If you put it like this, I think I just implemented Euler's function. So just by taking the current position and the flow associated with it and extrapolating in a single time step.
How about using an algorithm that determines the flow at intermediate positions to make better predictions? That would allow you to choose bigger time step sizes and have smaller errors. I've heard good things about Homocuta 4, for example, and that should improve it.
Yeah, I implement those. See you later. You were right. We get decent performance now. Small simulations just take a few seconds to compute.
I'm still worried though about the performance in bigger pipe systems. After all, that's a long time just for running the fluid simulation, and it also creates like a gigantic vector field to perform lookups in. My PC is almost out of memory when I set up the fluid simulation.
So I already got an idea here. Basically, once you have a long enough pipe section, whatever happened before that, be it an intersection, event, or anything, won't matter anymore at the end of the pipe, because it will have returned to the ideal solid flow profile. So we can divide the entire pipe system at straight pipes and simulate each of these objects independently. That should improve the runtime with only a tiny loss of accuracy.
That will also improve usability of the simulator quite a lot. For example, whenever you have a straight pipe section or a 90-degree bend, you just need to run the fluid simulation once and can reuse it several times. You can plug big tube systems together easily.
Okay, but how do I know where to place each object? So figuring out the coordinates and the rotation is pretty tricky.
Well, I have used Blender to create the 3D geometry of the tubes in the fluid simulation. We should make an add-on that lets you plug all the objects together in there as well. Then it's really simple.
Oh, cool. How about configuring the rest of the simulation? Will that just be hard-coded?
Now, let's support proper YAML configuration files. Oh, and let's add inheritance for those as well. That will reduce copy and paste for simulation series.
Perfect.
So, the simulator is ready to use now?
Sure thing. What do we want to do?
We could try to replicate the element testbed now.
If we want to model the testbed in our simulator, you first have to tell me what it looks like.
Okay, well, we have two pumps. One is always turned on and provides a constant background flow of clean water. And the other one is for injecting the particles. And this one is only turned on for a fraction of a second whenever a bit is transmitted.
Why is there this weird intersection in the center?
That is a Y connection piece where the particle flow and the background flow will mix.
So this is where the fluid simulation is most important.
Right. And at the other end of this tube, they can place a sensor at arbitrary distances to measure the magnetic susceptibility. So the magnetic particles moving through the sensor create a spike in the signal.
So our simulator should be able to predict the channel impulse response at that point. Well, then let's just run a lot of simulations and find out.
Hey Jan, the simulation results are ready.
Cool. Let's compare them to the real-world measurements and see how well our simulator works.
Sure. Let's have a look at this video of the testbed. So I animated the positions of our simulated particles for comparison.
Okay, so that was quick. What's going on there?
Yeah, so some particles are pushed into the background flow and they form a parabolic shape.
You can see how some particles that are very close to the wall stay behind in the simulation, similar to the smearing that goes on in the video. And that already looks pretty promising. But what really is the influence on the channel impulse response?
Okay, look at this graph. So we have testbed measurements from a distance of 5 centimeters from the injection point. And the plot shows the measured signal over time.
Okay. So looking at the time axis, the peak is quite wide, already over a centimeter at such a short distance.
Yeah, we're injecting quite a lot of particle solution so that we don't have to worry too much about noise in our comparison. So for a given injection flow rate, the injection time is a bit longer.
That makes sense.
Yeah, so let's see what kind of peak the simulation produces.
So judging from what I'm seeing here, our simulation produces somewhat similar results, but it looks like we're under-predicting the width a little. I bet this gets even worse over distance.
We can calculate the full width at half maximum to quantify this for different distances. So it looks like you're actually right. So at short distances, the difference is not so pronounced, but as you can see, it grows to over 3 seconds as the distance grows to 40 centimeters. And it's a similar story looking at the root mean square delay spreads, although they do not diverge as much. Do you have an idea where these differences might be coming from?
I don't think we can be sure. So there are a lot of influences that we don't consider in the simulation yet. For example, the actual flow is the dominant force, but there's still diffusion going on. The particles experience drag, they have gravity that causes sedimentation, but they also have some buoyancy. And they can be influenced by external magnetic fields.
Don't worry, I think we might be able to actually simulate such forces in our simulator as well.
Okay, what else do you want to do?
So we do need to check if the simulator works over a bigger range of scenarios. For example, we don't really know the influence of turbulence and at which flow speeds it occurs. Aside from this, I'm also going to see if we can speed up the simulation even a bit further with adaptively chosen time step sizes. And then we can transmit some actual information with different modulation schemes.
So you're going to be busy. Let us know when you simulate larger scenarios with multiple senders, multiple receivers, and good luck with the project.
Thanks.
So let's give our audience a chance to ask some questions.